Okay. Morning, everyone. My name is Thomas Shen. I'm here to represent Professor Kadowski for his talk. Unfortunately, he cannot attend this workshop in person. So I gotta apologize in advance if I cannot clarify some of the points here clearly, because some of the work here are not by myself, but I will try my best. So the topic of my talk here is the Ultraflow access networks, a novel and a powerful dual-mode approach. So first of all, we would like to thank our partners and sponsors for their great contribution to our work. So this is the outline of my talk. First, I will give some introduction about the Ultraflow access network and its concept. Then we'll go through some details of the design. Following that, I will have some experiment results we have on our testbed, and then I will conclude the whole talk. Okay, first of all, introduction. So basically, what's Ultraflow? Ultraflow is a comprehensive research project on the optical flow switch network. And then what's OFS? OFS basically is kind of new network architecture that schedules a end-to-end dedicated path before the transmission starts. And because of that, no electronic and buffering are involved during the transmission. And such characteristics give OFS or Ultraflow network certain advantage, including no throughput limit from electronic processing speed, low transmission overhead, especially for large files, and energy efficiencies. We have all these advantages compared to a conventional electronic packet switch network. Of course, to achieve all these, we have certain challenges here, and I will address some of them later in my talk. Okay. This graph captures the general concepts of our Ultraflow access concept. So basically, as you can see, we are not removing the IP service, but we're trying to introduce the new optical flow service alongside it without interrupting all the existing services. And if there are some already IP PON technology deployed, such as EPON or GPON, then we hope our new Ultraflow service can collaborate with these deployments and probably share the same infrastructure to reduce the cost and improve the efficiency of the network. Then I will discuss some of the details of the Ultraflow access network. So this is the general architecture of an Ultraflow access network. We have 3 addition nodes here compared to a conventional IP PONs, namely OFNU, Optical Flow Network Unit, OFLT, Optical Flow Line Terminal, and gateways. So OFNU and OFLT are the counterparts of ONU and OLT for the flow service. They regulate and manage all the flow transmissions on the user premises and at the central office. And we have the gateway to separate the operating waveband of the IP channel and flow channel. And depending on the configuration or the specification of the transceivers at the OFNU or OFLT, the gateways may also be used to separate the upstream and downstream flow transmissions. This block diagram here shows the basic block functions of a OFLT. So basically, the OFLT is the brain of the whole Ultraflow access network. It controls and manages all the flow resources attached to it. And if OEO capability is enabled, then it may also do the dynamic wavelength allocation within the access network. It may also conduct certain flow channel monitoring to ensure the quality of service of the flow channel. This schematic diagram shows the OFNU internal function. It manages all the flow resources at the user premises, such as the transceivers and all those network adapters. Here is the design details for 4-port ONU gateways. So as you can see, it separates the operating waveband of the IP channel at 1310 and 4090 from the C-band used by the flow channels. And if we have only a very simple transceivers, then probably we can also, the 4-port gateways can also separate the upstream and downstream flow transmissions. But if given a more sophisticated transceivers, then probably we can combine these two and use a 3-port gateways to provide full flexibility, full access of the whole C-band access. And to ensure that our architecture is future-proof, we extend the previous simple architecture design to a more sophisticated, reconfigurable, long-reach ultraflow access network. So this new architecture is designed to work with all future and existing IP-PON technology, such as the XG-PON or NG-PON, NG-PON2, which may be deployed in a long-reach structure to serve more users in wider areas. And with two reconfigurable switching devices placed at the central office or at the remote node, we can reduce the capital expenditure during the early stage of the deployment, and we may also increase energy efficiency and improve the reliability for daily operation of the ultraflow access network. Then, having talked about the data plane, we move on to the control plane of the ultraflow access network. So, to achieve a really flexible, expandable, and efficient control of the ultraflow access network, we are working on a software-defined network controller that centralizes the IP and flow service, the control of these two services at probably one SDN controller, and the handling of the incoming packets are defined by the software control app. And by doing this, we can unify the control plane for the IP and the flow service. We may also isolate the ultraflow control plane from the data plane, which simplified the deployment and some possible future updates for the flow service. And also importantly, we can consolidate the IP and flow hardware, by which we mean we can use the same hardware for either flow or IP transmissions depending on the software running on it. And this can help us to lower the inventory cost because we have less diversity in the inventory. So because the ultraflow channel, the flow channel in particular, is really optimized for large file transmission, so we would not like to transmit some small packets such as the control message on such precious end-to-end dedicated channels. So we propose to send the control message over the IPs instead of the float channels. That's why we have the OFNU and OFLT attached to the IPONU and IPOLT through the Ethernet to gain the IP access. So the control message can be communicated in the payload of some IP packets destined for the SDN controller, or they can be embedded in the extended IP PON control message, such as the MPCP used in the EPONs. Sorry. Okay. So now let's go further up layers to the network stack. So there are two main goals for us to design a full network stack for the flow transmissions. The first goal is to keep the current TCP/IP stack intact so as to minimize the impact of the new service on the existing systems. And another goal is to optimize each layer here for the reliability and for reliable and flexible transmission of the flow files. And talking about the reliability, we also implement the ARQs, automatic repeat request mechanism, on our ultraflow access network. So before a transmission, each large file is fragmented into some smaller flow frames, and each flow frame is also labeled by some sequence number and session ID. The optimal size of the flow frames have been studied by our partners at MIT, so I won't go into any details about that, but here I'll just briefly describe the mechanism of the ARQ here. So whenever we have some frames lost during transmission, or they are so corrupted that FEC cannot recover them, then the receiver will send all these session number and a sequence number in a NAC back to the senders. And upon the receiver of these NACs, the sender will retransmit those packets. The whole process will continue until either the receivers receive the whole files or the pre-scheduled flow session expires. Okay, now I will show some experiment results on our test bed. So this is a detailed experiment, a block diagram for the simple version of our architecture. You can see that we have 3 ONUs on site. They are all independent computers attached to GPON ONU and GPON OLTs. And to test out, we also tried out different combinations of receivers with either fully tunable or fixed, with some gateways having either 4-port or 3 ports. This is to simulate a situation that in some networks we may have full tunable transceivers, while in the other we only have fixed transceivers to reduce the cost. And we want to see how that's going to impact the performance of the system. And to enable efficient intra-PON communications, we introduce a reflection median at 2 potential points to reflect the upstream flow transmission down to a receiver within the same PON without involving any resources beyond the PON domain. Here's a more detailed diagram for the reflection medium. We use OADM to separate the intra-PON and inter-PON flow channels, and the upstream channel is amplified and reflect back to the destination by a circuit and a SOA. This technique, however, comes at the expense of some reflection noise, where we study in more details here. So you can see this is on the left-hand side, we have a crosstalk to signal. This is a numerical study of the crosstalk to signal ratios. And on the right-hand side, we have both measured and calculated BER for different SOA gain. So the general observation is that the CSR will increase with fiber loss and as well as the SOA, but the optimal SOA gain is should be approximately the same as the fiber loss. And we also noticed that if we have a too high splitting ratio in the PON, then probably the loss will be too high or the noise will be too high to enable the error-free intra-PON communications. So this is the experiment test bed we used to test the previous mentioned reconfigurable long-reach ultraflow access network over 100 kilometers distance. And this is our BER measurements. So basically we verify that the architecture physically can support maximum 1024 users over a distance of 100 kilometers with all those reconfigurable devices in between. So having tested our data plane, now we move on to the demonstration of the control plane. So we have 3 individual computers. 2 of them are OFLT and OFNU integrated with the file server and a web browser plugin respectively. And we have a flow service control, the SDN software-defined controller on another independent computer. And all these 3 control units are connected through a local area network. And the the channel in between the 2 computers are actually the connection between the XY and X point and Y point. So basically, the whole process that we have, the users can send a download request to the file server through the web browser. Then web browser plugins, and after several rounds of communications, both parties will send a flow transmission request to the OFLT and OFNU respectively. Then OFLT and OFNU will both send some requests to the flow service, which will schedule a flow session. And when the flow sessions approach, both parties start transmission. We successfully download a 9 gigabyte files from the server to the users at a throughput of 9.8 gigabits per second, which is approximately the theoretical value we have, because with the transceiver we use is 10 gigabits per second. So basically here is just a more graphical description of what I just described to you, the process of the whole control plane demonstration. And finally, we also did some tests, ARQ tests, to test the performance of implementation subject to different BER and the flow frame size with no FEC. And we gauge the performance using a metric called effective channel throughput, which is a ratio of the flow file size over the total transmission time. And we introduce artificially introduced some burst errors in the software level with the parameters proposed in this reference here. And here are the results. So some observations that ARQ is the flow files, the larger flow frames is more vulnerable to burst errors as expected, while the smaller flow frame size is more resistant to both the errors and change in and also the burst error frequencies. So, which means our flow frame size is limited by the burst error, or in turns the retransmission times. But if a flow frame is too small, then basically we'll suffer from too much overheads. So we need to balance the retransmission time and the overhead of the flow frames. But of course, if the channel is really loud, noisy, then we need to employ the FEC to ensure the channel quality. Okay, so finally, conclusion. So the Ultraflow access network is more efficient for large file transmission, and it enables both IP and optical flow service. And with the reconfigured long-reach Ultraflow access network, the flow service can coexist with existing and future IP PON technologies, and it can serve more users in a wide area. And with those reconfigured devices, we can make it more cost-effective and energy efficient. And also the SDN controller enables to centralize control and management of both IP and flow service that simplify the deployment and the future updates, and also unify the hardware of IP and the flow channels. And from the experiment results, we know that the new long-reach configuration can support 1024 users. And we also successfully demonstrate the idea of the SDN controller. And we also test out the ARQ performance and find out that we need to balance between the retransmission time and overhead. And if the channel is really bad, then we need FEC to maintain the channel qualities. Thank you.